So this is 1.2 mock revision update. So let's have a look through this. Right, so going to go through these things. Let's do it now. So we've already sort of talked about primary versus secondary storage, but I'll quickly recap. So primary storage is faster, smaller capacity, and can be spoken to directly by the CPU, accessed directly by the CPU. And obviously the opposite is true for secondary. Just remember that I wouldn't say it was slow, just not as fast as main memory. I mean, speed is relative, but I don't know. But it's not slow as such, just not as fast as main memory. Has a much larger capacity, and it cannot be directly accessed by the CPU. There are three main types of secondary storage: optical, solid state, and magnetic. If the question in the paper asks you to name three types, don't name solid state drive. That is not the type, it is solid state. A solid state drive is an example of a solid state storage. So look, you can just read on the screen what they are, so I'm not really going to go through them too much. But optical, cheap, easy to post, low storage. Solid state, fast, large capacity, expensive, robust, and small physical size. It also doesn't have moving parts, which is quite good for things like a mobile phone. Okay? And then magnetic is large capacity, cheap, and cannot be moved around easily. If you do get a question when comparing, say, like this and this or whatever, don't forget to mention large capacity. A lot of kids will sort of only mention the differences between things and not the similarities. So don't forget, if you ever compare magnetic and solid state storage, don't ignore the bits that are similar. Right? Anyway, let's move on because you can read that. So, how is sound stored on a computer? Well, sound is stored on a computer in binary, right? A recording is taken from a microphone, and samples of the analog wave are taken at set intervals. This is called sample rate, and it's measured in hertz, which I should have probably put on there, hertz, which you should know. The accuracy of the sample is defined by the bit depth, and the higher the bit depth, the more accurate more accurate, but a larger file. The more samples you take per second, more accuracy, but larger file size. So if you want to do a pictorial representation, this would be a low bit depth. Now, what bit depth means, how many bits are being allocated to each sample. So here we're allocating 2 bits, which is obviously ridiculous and wouldn't even be realistic. So that means when you're taking a sample, you literally have, if you've got two bits, the samples can be that. So we've got to turn each of these into 0, 1, 2, or 3. So obviously this sample here would be, I don't know, let's be 1 and 2, but we'll say 1. That will be 2, probably rounded down to 2. That's 1 again, 2, 1, 0. So this would end up being 1, 2, 1, 1, 2, 1, 0. You can see here that and if I then redraw that out, which is what would happen, I would end up with 1, 2, 1, 1, 2, 1, 0, and I would end up with this, which doesn't look, it looks a bit like that, but you've realized that you've completely changed what the sound looks like, and it's not very accurate, and the heights are all different. Whereas here, if you've got a higher bit depth, this would actually be 8 bits, so we can go from anything from 0, 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1. So that would be 0 to, I won't put the minus because you might get confused, 255. So we've got 256. Well, now I can start saying, I'm just going to guess random numbers, like 111 or something, and that's 201, and that's 120, and you know what I mean? We can take a more 123. We can take a more accurate sample. We'll end up with a more accurate, reading at the end or whatever, because we've got a higher bit depth. And again, sample rate would just be taking more samples. If we took more samples, then of course we would also get a closer representation of the file. But of course we would have more numbers, and more numbers is bigger file size. So that's how sound is stored on a computer, in binary, in samples taken per second. And the bit depth is how many bits you allocate to each sample. And so if you've got a lower number of bits, you've got a lower number of options. And it's got to have one of those options. Right, there we go. So let's move on to binary. Why do computers use binary? Well, computers use binary because they're made up of transistors, switches, which can be in 2 states. And we call them off 0 and 1, but technically they're off and on switches. There's no actual 0s and 1s in the computer. It's just how we conceptualize 2 switches to be 0, off and on. And so here, you've just got to remember that the right number starts at 1, as it does in all number systems in the West. And then you double each time as you go across. So this is going to be 21. Because you've got a 1 under the 16, a 1 under the 4, and a 1 under the 1. I'm not going over that too much because we've covered that many times, and you can find many videos on that if you're confused. So let's do binary addition, which is the one that people struggle with the most. Although it isn't actually, in my opinion, very difficult. You just got to, if you understand binary. Right. So 1 plus 1 is 2, right? So you can't write 2 because 2 don't exist, right? You've only got 1 or a 0 to write. And so to write 2 in binary is 1, 0, right? 1, 0. Now we don't write 1, 0 in here because that's stupid. You don't do that in math. You carry the 1 over. So you're writing 2 in binary, yeah? Because that adds up to 2. That adds up to 3 now. 1, 2, 3. And 3 in binary is 1, 1. So I write the 1 there, which is this one, and we carry the 1 over. Now I've got 3 again, which I know is 1, 1. Now I've got 2, which is 1, 0, because that's the 2 for binary. So I put 1, 0. We've got 2 again, 1, 0. We've got 2 again, 1, 0. We've got 1, that adds up to 1. We've got 1, that adds up to 1. And so that is the addition done. If you do get a number that goes over the end, like say this was 1, 1, 1, and we ended up with 1, 1, and a number goes over the end, this would be called an overflow, okay? And the computer's got to deal with that because basically it's gone over its maximum capacity for maths in that size. Obviously this is 8-bit, computers now are 64-bit, so numbers are absolutely huge, and that happens significantly less. And they can do clever techniques if it does anyway to still get the right answer. But they have to do something. That's the point. They have to know that it's overflowing. Because if you don't do anything, you're just getting the wrong answer. Like if you had 8-bit computer and you add 1, 1, 1, 1, 1, 1, 1, 1. Hold on, let's have a look. And you just add 1 to it. Well, obviously it's going to be, you're going to end up going over, and it's going to be a number the 8-bit computer can't understand. So overflows are important to understand. They happen, but they can be dealt with. But that's what it's called. So let's go to the next bit, which is hexadecimal. Yeah. So first of all, why hexadecimal? Well, this is an exact example, right? Years ago, they used to have to type things in binary, and the numbers would be like this, all close together, and it'd be very easy to get confused what you were typing in. And so hexadecimal, this is the hexadecimal version. So what someone thought was, wouldn't it be good? And I know I'll come back to that in a second. Wouldn't it be good if we could just have 2 digits that represent a byte? And that's what they've done here. So each digit here represents a nibble, which is 4 bits. Okay, I'll just underline it. No, I won't because I'm not drawing. So that is E, and that is 9. That is 4, and that is 5. That is 8. I think actually, yeah, sorry, I've gone too far there. Let's undo. That is 8, and that is 9. And I'll go through why in a second. So don't worry if that's confusing, although I have been through this in class. But it's probably a long time ago for some of you. So just understand, now a lot of students say, why don't they just turn it into the decimal number? But the problem with the decimal number is they have different numbers of digits. Like you can have number 1, 12, for example, has 2 digits. 150 has 3 digits. What they wanted was a way to represent a byte with 2 digits every time 2. Do you know what I mean? Just to be easier to read, really. Just remember, computers always store stuff as binary. What we see, like E9, is just a representation in a different number format. Just like, for example, you could say 3 weeks instead of 21 days, but it's still 21 days, no matter how many times you say 3 weeks. It's not 3, it's 21 days if that was, is the actual number of days. It's just that you can say it or show it in a different way. So why is this E9? Well, hexadecimal works like this. 0 to 9 are the same, okay, because they take 1 digit up. And then they need a digit for 10. So they use A, B, C, D, and like this. And the reason it's 0 to 15 is because 0, 0, 0, 0 is 0, and 1, 1, 1, 1 is 15. So they had a way to represent what's called a nibble, half a byte, 4 bits, with a digit. So they gave a digit to each combination, but obviously 0, 1, 2, 3, 4 to 9 already had appropriate digits. We can just use 0 to 9, right? And obviously when it gets to 10, which is 1010, they made that A. And then 11 was B, and then so on and so forth up to 15, which is F, right? So how do you convert them? Well, let's do the other way around, and we'll come back to that in a second. So let's say the exam paper says, what is F, am I even typing? F2 in decimal. Okay, so what you got to understand is this digit's worth 1, and it's hexadecimal. So this digit is worth 16. Just like in binary, it goes 1, 2, 4 because there are 2 digits, 0 and 1. Yeah. And in our number system, we've got 10 digits, which is 0 to 9. So it goes 1, 10, 100. Okay, so that's why, and that's times 10 because you have 10 digits. Well, hexadecimal has 16 digits, so it goes 1, 16, and it doesn't go on from that, but it's 256, but it doesn't go on. It only ever does 2 digits. All you got to remember is this is times C, times that by that. So 16 times F and 1 times 2. So obviously 1 times 2 is 2, so we'll ignore that. And then 16 times F, well, it's 16 times 15, which at first sounds difficult, but it's just 16 times 10 is 160, plus a half is 80. So 16 times 15 is 240. So that would be 2, 4, 2, because you do 16 times that plus that. So let's do another one. Let's do 4A. So again, this is worth 1, this is worth 16. So 4 16s are 64. Okay, 1A, which is just whatever this is, so it's 10 plus 10 equals 74. Okay, so there you go. That's how hexadecimal from this would work. Like if you're going from hex to dec, which is what we call our system, the decimal system, hex to dec. All right, hexadecimal decimal. Right, other way around. I mean, it's you can sometimes you get like right 38 as hexadecimal. Well, the thing is, how many 16s go into that? Well, 2 16s are 32, so I've got 2. Remember, that's worth 16, this worth 1. And I've got 6 left. So 2 6. As hexadecimal would be 2 6. Because remember, 2 times 16 is 32, plus 6 would be 38. So it's very rare they ask that way round to convert from decimal to hexadecimal. But it's just common sense, really. If they gave you a number, for example, 169, then you think, right, how many 16s go into that completely? Well, hopefully your brain will tell you immediately it's 10. So you got a number of 16s, and we've got 9 left, so that'd be A9. Okay. Now, more common is this. They'll give you a binary number and ask you to turn it into hex. So let's take that binary number away from there. And what you do is you split it in half. And you write 1, 2, 4, 8. 1, 2, 4, 8. Add them up. 8, 2, and 4 is 14, which is E. And 8 and 1 is 9, which is just 9. So that's how I got E9 from before. So let's do another one quickly. I don't even know. I'll take a completely different number. I'll take like random one from here. There's not a number. That's not one from before. So that is, remember to split it in 2. Obviously that's 1. I'm sure you can realise that's 1. Right, and that's 1, 2, and 8. So that's 11. Okay, 11 is B. So that would be B1. That number there. The answer would be 1. Okay. Now, if they do the opposite, if they give you some letters and ask you to turn it into hexadecimal, so let's say they give you EA Sports, then you just do them separately again. So E is 14. So we write 14 out in binary. So 8, 4, and 2 makes 14. So that's E. And 10 is 1, 0, 1, 0. And if you don't know what I'm saying, then I'll put the digits up. But I can do it from memory. And you should start to get to the point where you can. So 2 plus 8 is 10, plus 4 is 14. And E is 14. A is 10. 8 and 2 is 10. So that would be the binary for hexadecimal. There you go. Right, so I've done that. Let's go on. If you're ever confused by these, I have got more in-depth videos on the web, but of course they're longer, and I wanted to try and keep this short for you. Right, so I'll keep it under 15 minutes. So let's quickly go back and look at the exam questions. So Kerry has 5 gigabytes of files transferred from a laptop. She has been told to buy an external solid-state drive to do this. Give one example of a solid-state device. Solid state. That's what I've answered already. So solid-state drive. You also could have flash drive. I mean, obviously, I'm not going to put anymore. If it ever says give one example, they'll always mark the first one. They won't mark any more. If it says explain or whatever, then yeah, whatever. Anyway, this is an example, obviously, of secondary storage. Remember, ROM and RAM are the primary storages. So that's an easy one, right? Digital video camera has secondary storage. Oh, William is creating a film for school. Right. Answer why digital video camera needs secondary storage. Okay. Primary storage that you can write data to, like RAM, is volatile and does not, volatile, meaning you lose the data if you turn the camera off, and does not have a large enough capacity for lots of films. Secondary storage has a large capacity. I know I'm saying the opposite, always do though. Capacity, and is non-volatile. Data not lost. There you go. Primary storage. Primary that you can write to, like RAM is volatile, meaning is because remember you can ROM is read only. It's non-volatile, but it's read only. So useless in this situation. So explain why solid state is the most appropriate type of storage for digital camera. So this is the answer that kids used to say. Solid state drive has solid state storage, has no moving parts, and as a digital camera is like, I'm going to just slow down my typing. Moved around, it is not suitable to have parts banging around or something like that. Now, the problem is people then forget the other bit. It's 4 marks here. So what? I've got about 4 marks. That's 1 mark. Okay. Solid state has a large capacity. Mark number 2 is reasonably fast. Number 3, and is very durable and robust. All things which are required. What did I say there? Robust. All things are required in a digital camera which is moving around and needs holding. I'll put an extra one as well. Solid state is also physically small, which also is required in a digital camera which will be held. I know I'm writing a long answer there, but I'm just trying to show you all the things that you could say. But just remember, it's 4 marks. So afterwards, mark yourself, right? No moving parts, and it's likely it's been moved. Don't just say it has no moving parts. Why is that useful? Because the digital camera gets moved around, right? Solid state has large capacity, is reasonably fast, and is very durable and robust. All things require a digital camera, which is moving around, need lots of holding. I'll put storing large video files as well, which is important. I probably could have worded this better, actually. I probably should have said, like, so other than that, large capacity, useful for large file sizes in videos. It would have been better to have done like this. Robust device in case the camera is dropped. Solid state is robust in case the camera is dropped. More like that would have been better to have actually written it. So I'm answering the reason for each one specifically next to it. I could put loads more. Small physical size will mean the device can be held in hands easier. It's handheld. So for the things like that, I think the one I said now was fast storage needed for when recording a video. Solid state fast. Make sure to state that as well, because that's easy to forget. It's like, great, yeah, fast storage is needed, but we're saying why is solid state good? So there you go. And loads of answers to that. Right, so this one here, I'm not going to answer this massively. I'm just going to quickly bullet it. It's an 8 marker. And so basically she wants to transfer her file. So you've got solid state or optical. So you've got to look at portability. So if you've got these 4 topics, I'm not going to answer all of them. But what you would do is you want to compare the 2 really. So we look at portability, and obviously solid state is far more portable than optical, as the disc can take up more space than a flash drive. Although optical can be posted easily, so this needs to be considered. I would choose solid state, whatever, so on and so forth. And then I would probably do the next bit, portability. Obviously this is massive font. And robustness, solid state's far more robust than a disc that can get scratched. Capacity, optical doesn't have the capacity of solid state, and you can mention that. And cost, optical is far cheaper than solid state, and overall solid state's better because you're worried about losing the data and various other things. So you could talk. It doesn't say you have to talk about those things, by the way. You may want to. So you could talk about anything afterwards, but that's how I would word that one out. So there you go. That's that one.